Hey guys, we're going to talk more today about the normal curve, specifically about finding percent area underneath the curve, and also finding a data point or even the mean if we know the area under the curve that we're interested in. So we talked yesterday about the SATs and this notation here that says we have normal data with a mean of 500 and a standard deviation of 100. And we tried to find a percentage based on a specific SAT score. So now we have a percentage given to us. So this college admits only people with an SAT verbal test score among the top 10% of all people who took it. So we want to figure out, hey, can we get into this college and what score is it going to take? So we should always draw a picture. And our mean goes in the middle of 500. Standard deviation is 100, so we can go up by 100s. We're going to go 3 in each direction because 99.7% of the data, if it's normal, falls within 3 standard deviations of the mean. And our top 10% is going to be somewhere up here on the right tail. So we're looking to find what is this area under, or we know this area under the curve. I'm sorry. We want to find out what is the SAT score right there. So I have a calculator here, and I can show you how we can actually calculate a z-score. So we're going to hit second and then the vars to get the distributions. And we're doing an inverse normal calculation, so we're going to use choice 3. Since the calculator calculates left-tailed percentages, we want to use 90% to plug into the calculator, because that tells us that from the left of this top 10% is the bottom 90%. So we'll plug in 0.9. Leave our mean at 0, our standard deviation of 1 since it's normal. We'll hit enter twice, and this is going to give us a z-score. So the z-score for this location on the graph is 1.28. And remember our z formula, we talked about it as x minus x bar over s. And since we're talking about a normal curve, we're going to use mu for mean and sigma for standard deviation, so this formula in green. And we can plug in what we know. We know the z-score. X is the data point we're looking for. What is the score that we have to achieve to be able to be admitted to this college? 500 is the mean, standard deviation of 100. We do some algebra here, multiply 100 on both sides, and then add 500, and we get a score of 628. So the SAT only reports in multiples of 10. So that means we're going to need to get a 630 or higher on the verbal portion to be admitted into this college. So I want to talk a little bit about reporting our findings in context and drawing a conclusion in context. We want to write something up formal here and say something to the effect of what I have written here, that the school requirement of scoring within the top 10% on the SAT verbal section means that the cutoff score, or the score that you have to achieve or get better than, is 630 in order to be admitted to that university. Okay, so you should pause here and take a minute and read this. You should pick out the important information, and then we'll pose a question for you. So the important things that we need to know, of course, is that this data is roughly symmetric, or the normal model applies. We need to know the standard deviation, and we need to know the average or the mean that we're going to use. So even though they want the mean to be 16 ounces, they have to set it a little bit higher to 16.3 so they're not underfilling the boxes of cereal. So we have a normal model with a mean of 16.3 and a standard deviation of 0.2. We want to know what fraction of boxes will be underweight. Remember that underweight is under 16 ounces. That's what they want their mean to be. So we need to find a z-score. Our data point is 16. because we want it no less than 16. Our mean is 16.3, and our standard deviation is 0.2. So when we calculate that out, we get a negative 1.5 z-score. We should sketch a picture here, and you can see that my pictures are not pretty. Just a sketch, something to help you out. 16.3 is our mean. Standard deviation means we go by 0.2, so down to 16.1 is one standard deviation, 15.9, 15.7. And the mark we're looking to hit here of 16 is somewhere above 15.9. It's got a z-score of negative 1.5. And so we want to find out what is this left tail area percentage of boxes that will be under 16 ounces. So we can calculate that. Second, vars. We're going to do normal CDF like we did yesterday. We'll make our lower bound about negative 100. Our upper bound is our z-score, negative 1.5. Leave 0 and 1 for our mean and standard deviation. And so we get this decimal here, 0.0668. And here's some notation too. The area under the curve of a z-score less than negative 1.5, that's what we're looking at here, is 0.0668. So that's approximately 6.7%. So we can say that approximately 6.7% of the boxes will contain less than 16 ounces of cereal and be underweight. So the company doesn't like that. They want to reduce that percentage of underweight boxes to 4%. And so we want to figure out what should we set the mean at for this machine in order to make sure that no more than 4% of the boxes will be underweight. So this is the new idea, what we started with here today, where we're going to use a percentage to find a z-score. So we should draw a little picture. We don't know what the mean is. That's what we're trying to explore and find out. We're looking for we know the left tail percentage of 4%, and we're trying to find a z-score. So we're going to go to our calculator, second, vars, inverse normal, 0.04 is our percentage, leave the mean and standard deviation, and we get a z-score of negative 1.75. So we can use our z-score formula, plug in what we know. We know the z-score. We know that 16 is our data point. That's the number of ounces that we want to be above or at. 0.2 is still our standard deviation. And we're looking for the mean that will achieve a 4% number of boxes underweight. So we can solve to get that the mean should be 16.35 ounces. So we can draw a conclusion here that the company should set their mean to 16.35 ounces of cereal in order to ensure that no more than 4% of the boxes will be underweight. So if they crank up the mean from 16.3 to 16.35, they should be able to ensure that 4% of the boxes will be underweight. So one more quick thing here in terms of being normal. So we said that if the data distribution was approximately symmetric and unimodal, then we could say it's approximately normal. There's another way to test that, and that would be to actually enter this data into a list on our calculator. So we would do stat, edit, enter that data in, as you can see I've done here. Then we can do a plot. And we're going to do a normal probability plot. So it's this last choice down here. And then you got to choose your correct list. And we're going to make the y-axis the data axis. So these agility scores that we have here, I think it was for boys in high school, are going to be our y-axis. And our x-axis is actually going to be z-scores. So then if we graph, and you got to, in order to see this, you should hit zoom stat. If this is a straight line, then we can say that our data is approximately normal. But you can see that's not really a straight line, so we're not really quite sure if this data is going to be normal. It's not a ton of data. It would probably be easier to see if there are more scores, but this is just another way to test if data is normal. So again, you could look at a histogram and see if it's symmetric and unimodal, or you can create this normal probability plot, and that is again on the stat plots, and it's the last choice. Okay, so that's it for today. If you have questions, ask. Make sure you show me that you took some notes, and then jump on the practice.